Hello, everyone. Thanks for coming to the CITA seminar today. I'm very happy to invite Dr. Gergo Popping today to have a seminar with us. Gergo Popping started his academic career and received his PhD from the University of Groningen in Netherlands. And after his PhD, he started ESO fellowship and become an independent researcher. And after that, he took the MPIA fellow based at the University of Heidelberg. And now he returned to ESO as a permanent astronomer. Let me thank Gergo on behalf of the audience, because it's very late at night and Gergo is still like preparing the talk in his office. So maybe I should give time back to Gergo. Yeah, you can start.
Okay, thank you. Well, thank you first of all for inviting me. It's late, but it's not that late. Don't worry. It's 9 p.m. It's before my usual bedtime, so I'm okay. Let me try to share the screen. Yeah, you can see it, right? Okay, excellent. So, hi, indeed, I'm Gergo Popping. I'm a staff astronomer at ESO in Garching in Germany, where I work in the European ALMA Regional Center. So as you'll see, as I go through the talk, a returning theme will be ALMA, that have been thinking most of my career about, which is actually, it's funny that I'm at ESO because I spent most of my career doing theory and simulations, but nevertheless ended up at an observatory supporting observers. But I'm also noticing that this has made me become a bit more of an observer as we go. So that automatically changed slides. I don't know why. Anyway, I'll be talking about the spatial distribution of dust-obscured star formation in TNG50 main sequence galaxies. So what I will do in this talk, I will give a zoomed out overview of galaxy or star formation in the universe, how dust obscured star formation plays an important role. Then we look at individual galaxies and slowly go further, zooming in, looking at what we think ALMA will observe as it comes to the resolved structures of these galaxies. So I would like to start with a figure that I'm sure many of you have seen from the review paper by McDowell and Dickinson. This is a well-known figure, but if you think about it, this figure took about 2 decades to create, to get all the ground and space-based observations together to have a measurement of star formation in the universe from redshift 0 on the left-hand side of the figure all the way to redshift 8 on the right-hand side. And what's shown on the y-axis is how much star formation there is in a year, in a volume in a given volume in the universe. And as we now know, the amount of star formation in the universe increases up to a redshift of about 2 and then decreases again till its current day value. And like I said, we very easily talk about this, but this is actually 2 decades of research by many people, many different instruments to get to this particular result. And something that's less frequently shown is a different version of this plot from the same paper, showing the star formation in the universe, but now split between the infrared, those are the red points on the top here, and the UV, the green and then purple. And the takeaway point here is that this is the star formation that you would infer by looking at different wavelengths. So the UV is the emission that escapes the galaxies that is not obscured by dust, whereas the infrared is the emission that is obscured by dust, then re-emitted in the infrared. And as you can see, up to redshift 2, 2.5 or so, this has been quantified fairly well in the infrared and is actually the dominant source of the amount of star formation in the universe. Dust-obscured star formation dominates the star formation in the universe, at least up to a redshift of 2.5 or so. At higher redshifts, we don't know that much about dust-obscured star formation, but you'll see that that's an area where ALMA will play an important role. So just to very quickly focus again on this dust-obscured star formation, what happens in a galaxy. So this is a figure I took from a paper by Leindert Bogaert. The blue line that you see here is the is the SED of a galaxy at redshift 2.7 with this particular stellar mass, star formation rate. That's not really relevant here, but the SED of a particular galaxy if there was no dust. However, there is dust in these galaxies. Sorry?
Well, you
sorry, I didn't mute. I'm sorry.
Okay, I'll just continue. If there is dust in the galaxy, the emission here in the UV and the optical is obscured. These are the data points that you get here and re-emitted in the infrared, and that's the data points that you see here in the red line. So as you can see, it's a quite relevant contribution. So historically, how has this been measured? Now, I won't go back that far in time, but I first wanted to start with Herschel. So Herschel collected a lot of data in the late 2000s, early 2010s. And this is a nice figure from the Hermes collaboration showing what a patch of the universe looks like at 250 microns, 350 microns, and 500 microns. And every dot that you see on the image here in the center corresponds to a single galaxy. One is a bit redder, the other a bit bluer, etc. But these are all individual galaxies emitting radiation in the infrared, in the submillimeter, so contributing to this dust-obscured star formation. And it's with observations like these where you could actually quantify the brightness at these infrared wavelengths, for instance, this particular one or this particular one, that you could actually start to construct what the SED of the galaxy looks like in this infrared regime. And then finally go to a plot like this, where you really know what the contribution of the dust-obscured star formation is to the star formation in the universe. If you go back a little bit further in time and to slightly longer wavelengths, then we enter the submillimeter regime. So this is a beautiful, groundbreaking image taken with scuba in the late 90s of a large submillimeter structure on the sky. Now, nowadays, you would say these are just big blobs, but this was really an important image as it showed us that there is objects there that are emitting very brightly at a submillimeter, millimeter wavelengths, which is this cold dust re-emitting. Now, just to put everything in perspective, because that will be relevant later on, the image here has a beam of about 14 arc seconds, or PSF of 14 arc seconds, depends on what background you have. And back then, in the late 90s, this was really revolutionary. Now, what do you do when you have big blobs, so to say, of bright emission, and you only know how bright they are? And essentially what you use, you just count them. And this is exactly what people did. They counted how many sources over an area of a sky there were with a particular brightness. And what you get is a plot like here on the left-hand side. These are called number counts, where on the x-axis you have the brightness, on the y-axis you have the number of objects that have at least that particular brightness over an area of the sky. And as you could expect, just like a normal luminosity function, as you go to fainter objects, there's more of them on the sky. So this is what the submillimeter community has been doing for quite a while, and they build new instruments to do this. And this has been really relevant to sort of quantify how big the contribution of dust-obscured emission really is, what type of bright beasts there are really out there, forming massive amounts of stars. But the observations were not very deep, not really sensitive. And as I mentioned before, with a beam of 14 arc seconds or so, what you quickly run into is source confusion. That within one resolution element, there's actually 2 or 3 sources all contributing to the brightness that you measure within that resolution element. So this is where ALMA really came in as a game changer for many fields, but also for extragalactic astronomy or high redshift galaxy formation and evolution. ALMA, compared to what there was out there, has a superior sensitivity, has superior angular resolution to avoid source confusion, and we can achieve angular resolutions of sub-arcsec or even milli-arcseconds, which means that you have the angular resolution to even resolve individual galaxies. So one of the first things that ALMA did once it started to allocate large programs was a large program called ASPECS, the ALMA spectroscopic survey of the Hubble ultra deep field. So what we did in this survey is that we targeted ALMA for about 150 hours on the Hubble Ultra Deep Field. There were multiple science cases. One of them, the driving one maybe, was to look for CO emission lines to measure how much molecular hydrogen there is and translate that into the molecular hydrogen density of the universe. There were science goals related to measuring to finding atomic or ionized carbon in galaxies. But also a relevant science goal was dust continuum, trying to fill these number counts to fainter sensitivities. And we picked the Hubble Ultra Deep Field on purpose because this is a very well-known area of the sky, because it was covered by so many other instruments, ground and space-based, with MUSE and HST GRISM spectroscopy, many sources for which we have spectroscopic redshifts, which essentially means that if you find a target in your ALMA data, there's a lot of ancillary data out there to reliably say this is the galaxy that this emission belongs to, and put these observations in context. So I'll just show you a beautiful result. I think it's a beautiful result. So what I said is we spent 150 hours looking at the Hubble Ultra Deep Field. Of these 150 hours, we spent about 80 of them in band 6, which corresponds to a wavelength of exactly of 1.1 millimeters. And the weather was favorable when this data was taken. And what that gives you is a millimeter map of the Hubble Ultra Deep Field at a depth of just below 10 microjanskis. Now, for those of you that are in the field, it's having a depth of 10 microjanskis for an area of the sky of about 4 square arc minutes is really breathtaking or groundbreaking. It's really, really new territory to go so deep over, for some millimeter standards, a fairly large area of the sky. And what you see on the left here is the beautiful map, and then every bright source here is the galaxy that is being detected. I mean, you already see many very bright ones here, also some fainter structure, etc. And just to put it in perspective, on the right-hand side, what you see is an image showing the area on the sky that ASPECS covered versus the depth. And then you see that over same areas were almost an order of magnitude or half an order of magnitude deeper. Which means that once we start counting these galaxies, we can go further, trying to measure the number counts. So this was the situation before ASPECS. These are 1.2 millimeter number counts. This regime over here, all above about 0.5 millijanskis or so, corresponds to most of the work that had been done earlier with single dish telescopes. And then once you go to fainter ones, what you see is mostly work based on lensing, where lensing was used to reach faint, to target faint objects, but it requires good knowledge of how the lensing actually works, or it requires a good lensing model and has a systematic uncertainty with itself. And now what we add here are the ASPECS number counts. So these are the black circles that you see over here. So we go down to about 0.05 microjanskis or so, no, millijanskis or so, excuse me. But as you can see, the error bars are really small. And these are just the direct detection. So really counting the galaxies that we reliably measured with a signal to noise ratio of at least 4.5 or so. And then what you see, is that you clearly see this flattening where the number counts start to turn over. We did an independent analysis as well, where we're not just counting the galaxies, but doing a careful evaluation of the noise in the ALMA cube. For those of you that are interested in technically how that's done, we can talk about it later, but essentially you're inverting half of the data, and in that way you're filtering out the real signal to get a good description of what the noise of your galaxy of the map looks like. And then once you know exactly what the noise looks like, you can recover what the real signal is. So let me put a big line over it to sort of better represent what it looks like. And then the cyan here is a model that we built to also describe this. And there's a number of relevant takeaway points here. First of all, If we would have added another 100 hours or so of observing time with equal conditions, we would have only detected a handful of more galaxies. Because the number counts are turning over, as you go fainter, you're not picking up many more galaxies anymore. This also means that we've recovered, we think, at least 93% of the extragalactic background light. So most of it. And then what that means is that at that point, at this wavelength, you can actually start to ask yourself, well, which galaxies contribute to the extragalactic background light and how? And here it is again relevant to remember that ASPECS was carried out within the Hubble Ultra Deep Field, and we know the properties of most of the galaxies that we detect with ALMA. So before showing that, this is just a slightly nicer representation of the same figure from the review paper by Jackie Hodge and Elisabetta da Cunha, where you see this turnover, and in ASPECS we go down this far, and at lower sensitivities, these are from lensing surveys. But because we know so much about these galaxies, what we can start to do is break these number counts down in various bins, focusing on galaxies at redshifts between 1 and 2, or 2 and 3, and 3 and 4. So that's what's done on the top left panel over here, where we can actually see how the various redshifts contribute to the black, to the full number counts. So the shaded area are the data.
Gergo.
Yeah.
Can I ask you a question? So you're essentially, this is the source number counts that you predict from illustrative simulation, right? Or...
No, I'll get to that in a second. So the shaded area that you see is the number counts that we've observed. And then the lines over here is from a model that we developed. So what we did, we used a universe machine from Peter Baruzzi, which is an abundance matching model, where which is essentially based on observations. You empirically determine how what galaxies live in what halo, but you can also follow the growth of individual galaxies. And by using additional sets of empirical relations, you can actually then also make a prediction for what the star formation rate is of these galaxies, or even what the dust mass is of these galaxies. And once you know how many UV photons there are in the dust mass, then you can actually work out how much emission is absorbed and how much is re-emitted at various wavelengths. So that's what we did here, and it gives you the lines. And as you can see, these models describe the redshift bins, for instance, fairly well. Similarly, in the bottom right, what you see, the shaded area are the star formation rates of the galaxies. So the number counts in bins of various star formation rates, and again, the solid lines, a model describing this. And here in the bottom left, the same idea in bins of stellar mass. So the black area is all the galaxies, and the green, orange, blue is various bins of stellar mass. And the models describing the observations slightly less well, maybe. But the takeaway point here is that now we've come to a regime where it's not only, let's just count how many bright objects we have. We can count how many there are, but we can start to place these in bins of stellar mass, bins of star formation rates. And the next step would actually be to make scaling relations. What is the dust continuum emission of a galaxy as a function of its star formation rate or stellar mass, for which you maybe want samples of a few hundred of galaxies or so. But even now with these type of models, and this is a very similar model, but from Jorge Zavala, what you can start to do is describe the data at various wavelengths. In the model, play with a number of parameters, like how much dust obscured star formation is there really, and fitting the data to these observations, and that way work out all the way to redshift 4, 5, 6. So well beyond what we've done so far with Herschel, what fraction of star formation in the universe is dust obscured, and what fraction of star formation in the universe is not dust obscured, as a function of redshift, going out to fairly high redshifts. And admittedly, the uncertainty range is fairly large, so half an order of magnitude or so, but we're really going into a new regime, quantifying this at a level that was not possible before ALMA. So to push this field further, going significantly wider or deeper in cosmological fields is actually already now in a way limited by ALMA's capabilities. The field of view of ALMA is unfortunately fairly small, so multi-square degree surveys on the sky will be complicated. You will need a very large single dish observatory to do that. That is sensitive as well. But still there are steps to make. The samples that we're looking into here are not very small, and you could do targeted samples. We already know that going much deeper will just give you a handful of objects. So you may want to follow up many individual galaxies, do better cross-matching with other galaxy properties. So you can really focus on individual galaxies and their scaling relations. But a different avenue is actually really zooming into these galaxies. So why are sizes relevant, or the locations of star formation, or the structure of galaxies? Why is it relevant? I'm sure many of you are aware that the size distribution of galaxies and how it evolves over cosmic time actually gives you quite a lot of clues about how galaxy formation happens and the connection to the dark matter, the galaxy halos the galaxies live in, how angular momentum is being transported into the galaxies. And again, over the last 10, 15 years or so, a lot of effort went into quantifying the sizes of galaxies in the optical and near infrared. I think a very well-known, well-cited paper is a work by Arjen van der Wel, and this is an image from his paper showing what the sizes of galaxies are, of star-forming galaxies and of quenched galaxies and various redshifts, and how they evolve over. And then you can ask yourself how they evolve over cosmic time. Galaxies grow, does the slope of these type of relations change, etc. But again, it's good to remember that especially at redshifts above 2 or so, the optical or near-infrared emission actually corresponds to, first of all, emission from young stars, but also emission that is being obscured. So you need this dust-obscured star formation component to really know where these young stars are living, where in the galaxies young stars are forming, to get a full understanding of at what locations in galaxies stars form, how this couples to where the stellar mass is located, or how this couples to where the gas out of which the stars form is located. So again, this is where ALMA comes to play. You need these sub-millimeter, millimeter observations to tell you something about where dust and gas is located. And ALMA was really designed sort of to resolve galaxy structure. For those of you, some of you may know this already, but the way ALMA works is that you have a large number of antennas. You have 50 12-meter antennas, and these antennas can be placed at different locations. So you can make a very compact array where you put all of them together in a small area. And then what you're doing, if you think about it just in lambda over d, you're making a small dish. So your angular resolution is maybe not so good, but you're sensitive. What you can also do is place the antennas very far away from each other. We call this long baselines. And this way you create a very extended observatory with baselines up to 15 kilometers. And again, if you take lambda over d, what this means is that the size of your instrument increases a lot, and you're able to resolve much smaller structures. So as I told you before, if you want to, you can go as far down as milliarc-second resolution. Now, for high redshift galaxies, this may be pushing it, but the takeaway point here is that with ALMA, you're really at the regime where you can look at these galaxies at a few hundred parsec resolution, or maybe even better. And I think that this is an area, a science avenue, that in the next couple of years, ALMA will need to push for significantly. In the last few years, there have been a handful of examples of resolved galaxies above redshift 1 or resolved main sequence galaxies. On the right-hand side, I'm showing an example from work by Melanie Kaasinen. This is actually a CO map, but what you see here is a main sequence galaxy resolved in about 3-4 resolution elements. And on the bottom panel, what you see is the moment 1 map, the velocity map. You can see some nice structure indicated, for instance, of rotation going on in these galaxies. But what we're hoping is that in the next couple of years, the number of these observations where we are resolving galaxies at high redshift, where we can precisely, even much better than in this particular example, where we can precisely tell this is where the dust and gas is located, this is where dust obscured star formation is happening. That's really an avenue that ALMA should pursue in the next couple of years. So what have we learned from the studies so far? I think one very relevant result is the following. This is again from a paper, from the same paper by Melanie Kaasinen. And on the x-axis, what is shown is the size of galaxies at 1.6 micron. 1.6 micron is here the stellar emission corresponding to a certain extent to where the stars are forming, or maybe where star formation is happening, but I will get back to that. On the y-axis, what you see is the half-light radius of the dust emission. And the takeaway point of this plot is that essentially all these galaxies, except for this one on the top, number 2, but all these galaxies have a dust size that is more compact than the size that you would measure from the stellar emission. So the dust emission is typically more compact than the stellar emission. And it has been hypothesized that this may be indicative of the buildup of a central stellar component, for instance. So, open questions are, why is the dust emission more compact than the stellar emission? Is this a common feature for galaxies, or only the really brightest objects that we've looked at so far? And then the sub-question of, is the dust continuum a good tracer of the molecular hydrogen at these resolved scales? Because we are actually quite frequently using dust emission to measure how much molecular hydrogen there is in galaxies. So this is where simulations can start to guide the way, because these observations are not there yet. So with the simulations, we can give predictions for what we think we will see and provide a theoretical context. So first attempt at this is from a great paper by Rachel Cochran, was what she did is she took galaxies from the fire simulation and then ran a radiative transfer code called SCIRT over these. And in that way, made mock images of these galaxies and measured the sizes of galaxies at various wavelengths. And what she found is that the dust continuum emission is actually more extended than the stellar mass distribution, which is slightly different from what we saw before with the observations that the dust continuum emission is more compact than the stellar emission. But these were just a handful of galaxies. These were zoom-in simulations, quite expensive to run, and really just a handful of galaxies. So the next step from a theoretical point of view could be, among others, statistical samples. And this is where Illustrious TNG comes in place. So I'm not going to go through a full overview of Illustrious TNG. Actually, Rainer is there, who knows much more about Illustrious TNG than I did, as he is one of the core developers. But I want to focus on a few takeaway points. So first of all, the Illustrious TNG is a cosmological hydrodynamic galaxy formation simulation that includes all the relevant bells and whistles for galaxy formation and evolution, accretion of matter onto galaxies, star formation, various types of feedback, metal enrichment, etc., etc. And this is all included as the new physical TNG model. But then what I want to focus on here is the following, is that this simulation comes in 3 flavors: TNG300, TNG100, and TNG50. TNG300 means a much larger simulated box at a decent resolution. TNG100 is a slightly smaller box at an increased mass resolution, and TNG50 is again an even smaller box, but with a mass resolution similar to zoom-in simulations. So what you have is a box of 50 co-moving megaparsec on the side with a mass resolution similar to zoom-in simulations. What this means is that you have the mass resolution to start to look at the structure of galaxies, at the resolved structure of galaxies, but within a cosmological volume, so for a large number of galaxies. And that's exactly what you want for, if you are asking yourself the question, how does the size of galaxies at various wavelengths evolve as a function of its stellar mass or metallicity, etc. So what we did is we took thousands of these TNG50 main sequence galaxies from redshift 1 to redshift 5, and then we post-processed this with the radiative transfer code SCIRT, which is developed mostly by Maarten Baas and Peter Kamps, to create mock images at various wavelengths, running from the UV all the way to millimeter wavelengths. So a relevant assumption that needs to go in here is, how do you actually assign dust? Because Illustrious TNG doesn't actually follow the formation and destruction of dust. But this is done by assigning a dust mass to a gas cell based on its metallicity. Because observationally and also in simulations that do include dust, we see that there's a clear trend between the dust to metal ratio of galaxies and their metallicity. And then what you get is, on the right-hand side, a few beautiful examples of galaxies at a wavelength of 300 micron and 850 micron. You see some nice structures, spiral arms, even hints of bars. And then the white circle indicates the half-light radius at these particular wavelengths. So what we did, we measured the half-light radii, various wavelengths, compare these to each other, or compare these to various baryonic properties. And then what you get is the following: a predicted mass-size relation of galaxies for the dust continuum. So on the x-axis here, you see galaxy stellar mass. On the y-axis here, you see the size of galaxies at an observed wavelength of 850 micron. And there's a number of takeaway points here already. So first of all, at all these redshifts running from 1 to 5, 1 in green and 5 in red, at all these redshifts, this relation is essentially flat. As a function of stellar mass, there's hardly any evolution in the median size of galaxies. There's some scatter, but there's not a strong relation with stellar mass. There is, however, a strong relation with redshift. From redshift 5 to redshift 1, at fixed stellar mass, the sizes at an observed wavelength of 850 micron increased by a factor of 3-4. But it may be good here to remember that at different redshifts, the same observed wavelength corresponds to different rest wavelengths. So you're actually tracing emission coming from a different part of the SCD, so to say. So it's good to ask ourselves the question, well, is there in simulations then actually a trend as a function of wavelength? The answer is actually no, there hardly isn't. So what's shown here is on the x-axis, the size, the wavelength that you're observing it. And on the y-axis, the size of a galaxy at that particular wavelength divided by the size at 850 micron. Left-hand and right-hand side are two different bins of stellar mass. And what you see is, sure, there is a bit of an evolution with wavelength, but it's only at the order of 10% or so. As you go from 500 microns to 2000 microns, the sizes of galaxies evolve maybe with 10–20% or so. So the changes that we saw before with a factor of 3–4 are not related to looking at different wavelengths. It's really the intrinsic size of these galaxies changing, which is actually also good news, observationally speaking, because if you would detect the galaxies at various wavelengths, you can still combine them together as one size, because from the simulation point of view, we don't expect a strong evolution. So the change that we see here with redshift is really indicative of the evolution of the galaxy this size in submillimeter wavelengths, not an SCD effect. So what does dust continuum actually trace?
Can I just interrupt real quick?
Yeah, sure.
Because you can also measure the half mass radius or the half light in unobscured, you know, if you just, because you can do that.
Yeah.
Is it evolving in the same way, presumably?
You're ruining my story here.
Oh, sorry. Okay.
No, it's perfectly fine. Those are excellent questions, but I'm building up to that. So what I'm showing you here now is, you know, because you can ask yourself the question, well, what does it really trace then, right? So on the x-axis, again, is stellar mass. On the y-axis is the dust size, the light size, the dust emission size, divided by the dust mass size. So the dust half mass radius. Okay. And then what you see is that this radius is slightly below 1, approximately 75 to 80%, but fairly flat, which means that actually the dust continuum emission of galaxies traces the dust mass of galaxies, the size, fairly well, certainly within the typical observational uncertainties that we have nowadays. We also know that dust continuum emission must have something to do with how much star formation there is, because you need to heat up the dust with energetic photons, and that needs to be re-emitted. So you can ask yourself, well, how does the dust continuum emission trace the locations of star formation? So again, on the x-axis, the stellar mass, on the y-axis, the half-light radius in dust continuum divided by the radius that contains half the star formation rate. And here what you see is certainly below stellar mass of 10 to the 10 or so, the ratio is essentially unity. As you go to higher redshifts, we see some big jumps, but this is actually really low number statistics. But certainly below stellar mass of 10 to the 10 or a few times 10 to the 10, the dust continuum size also traces the locations where star formation is happening very closely, which is in a way reassuring. We know that you need dust and we know that you need UV photons to get this emission, and clearly indeed where the dust continuum emission is located is at the same sort of regions. A next step would be to sort of have a pixel by pixel comparison, but that's for later. And then I very quickly, as an intermezzo, want to touch upon molecular hydrogen, because this is frequently used in the literature, using dust continuum emission as a tracer of molecular hydrogen. Is this ratio 1 also unity? So what's plotted here on the y-axis is 850 micron emission divided by the radius that contains half the molecular hydrogen. And then what you see is that at redshift 1, this ratio is roughly unity, but the scatter is quite large. And if you go to higher redshifts, this ratio actually drops to 75, 60, maybe even 50%. So there, especially towards higher redshifts, you need to be cautious. Now, there's a number of systematics here from the modeling point of view, because how do you model molecular hydrogen when you don't actually have the cooling networks to go down to 20, 30 Kelvin in the simulation? But that's a different topic. So I started with showing that the dust continuum emission is more compact than the stellar emission. So what I'm showing you here is galaxy stellar mass divided by, so on the x-axis and on the y-axis, dust continuum size divided by the radius that contains half the stellar mass. And what you see is two things. First of all, as a function of stellar mass, there's a clear trend. But second of all, what you see is that this ratio is, especially for the more massive galaxies, larger than 1, up to 1.5 or even higher. So the dust continuum emission is actually more extended than the radius containing half the stellar mass. Now, so far, you may or may not have noticed, I've been very careful in saying stellar mass versus stellar emission. Because what happens if you actually do the same ratio, but instead of, but now what I'm doing is I'm dividing it by the radius that contains half the 1.6 micron emission that you would observe. Then suddenly this ratio drops. It's around unity at redshift 1, and as you increase redshift, go further back in look-back time, this ratio is lower and lower and lower. So the dust continuum emission is, in the simulations, is certainly more compact than the stellar emission, but it's more extended than the stellar mass. So which means that something is actually then off between the stellar mass and the stellar emission, right? And here's where the simulations are beautiful. Because we can do the exact same exercise, but now we say, let's ignore dust. There is no dust in the galaxies. So you run skirt as if there were no dust. So what you're picking up is really just the pure stellar emission emitted directly by the stars. The ratio that you get is essentially 1. So this is again the ratio. So what I'm showing you here is the half light radius at 1.6 micron, if there's no dust, divided by the stellar half mass radius. So stellar light traces stellar mass very nicely. Now I'm adding in dust, and boom. Suddenly these ratios increase dramatically. As you go to higher redshift, the stellar emission is much more extended, or the half light radius is much more extended than the half mass radius. You can also take a look at an individual galaxy. So this is a galaxy at redshift 2. The top panel is when there is dust included in the simulation. The center panel is when there is no dust included in the simulation. This is the same galaxy. You already see that in the center galaxy, the emission is more compact. It's even a bit brighter in the center. It's the same scale. If you look at the circles indicative of the half light radius, it's also more compact. And in the bottom panel, what's plotted is the light profile. So as a function of radius, as you move outwards in the galaxy, how bright the galaxy is. And in green is when there is no dust, and in red when there is dust. And what you see, the moment you add dust, the central component is being absorbed. And therefore your light profile changes from this to that, or with two hands from this to that. Which means that if you measure a half light radius from here to there, your half light radius suddenly increases. So what you're looking at is that when you're adding dust, the 1.6 micron emission is actually extended because dust is obscuring the central components. And this is exactly where it will shine at dust continuum wavelengths, at millimeter wavelengths. This is the same example at redshift 5. It shows essentially the same trend. But then to put everything in context, what you're seeing is the compact dust emission is not necessarily the sign of a buildup of a central component of stars. We've seen that dust continuum very closely follows where star formation is happening. But what it's showing is that dust in the center is absorbing light at stellar emission, making it more extended, whereas it will shine where it was absorbed. And that's why you get these compact dust distributions. So it's really an effect of dust obscuration. And here's then a fun game that you can play. This is ALMA, but you could also ask yourself, can we see these type of effects with the next generations of instruments? You could think about the JWST, but also the 40-meter class optical and infrared observatories that will also, especially with adaptive optics, be able to resolve galaxies quite well. And so this is just really preliminary, a plot that I made just a few weeks ago for the fun of it. What's shown here is the size of galaxies when you have this dust at the wavelength that's provided on the x-axis, divided by the size at 1.6 micron. And what you see is that indeed, as you go through wavelength, you see a change in size. And if you ignore dust, then this ratio is roughly 1. It actually evolves a little bit. But you certainly do see dust obscuration effects, especially towards the shorter wavelengths, which is what you would expect because this is the bluer emission. In this example, you even see the bump of the extinction curve, which is quite neat. And if we could do that observationally, that would be really exciting. But maybe systematics will start to play a role there. So I would like to conclude, first of all, by saying ALMA is great. ALMA is really revolutionizing what we know about galaxies, about many fields of astronomy, but what we know about galaxies, about dust obscured emission in galaxies, or dust emission in galaxies, also a lot about various molecules, atoms. It's relevant for chemistry, for many different science topics. But what we see in these models, and I'm focusing here on the last part, is that the dust continuum emission that we expect to see, once ALMA will provide more and more of these type of predictions, is that the dust continuum emission of main sequence galaxies is indeed more compact than the 1.6 micron emissions, but it's more extended than the stellar emission. And this is really due to the compact dust distribution driving dust absorption of the optical and infrared light. It's not necessarily the buildup of a central component. And then dust continuum emission is not necessarily a good tracer of molecular hydrogen half mass radius, but I would really like to finish with the last sentence, the forward look. The models, and I'm not the only one playing these games, there's more of us. The models are really ready. And sure, they can be improved, but a big step forward would be future ALMA observations or JWST observations, adaptive optic ground-based observations that will be able to start to confront these predictions, right? That will prove us right or wrong. Going into new parameter space towards lower masses, higher redshifts, lower metallicities, and eventually not even only looking at just what is the size of a galaxy, but doing a pixel by pixel, or 100 parsec by 100 parsec comparison of how emission at various wavelengths corresponds to each other, what this tells us about where star formation is happening and how the fueling of star formation happens, or how metal enrichment works, etc., etc. The models are there. The instruments are there or are currently being built, launched. So I'm expecting a lot of exciting results in the next couple of years. And with that, I would like to finish and thank you for your attention. And I'd be happy to take any questions you have.
Okay, thanks, Gergo, for the very informative and interesting talk. So this is the question time. If anyone has questions, please raise your hand. I see. Okay, Norm.
Yeah, thanks for a great talk. And sorry, I jumped in the middle there. You did answer.
That's fine. That's perfectly fine. That's perfectly fine.
Yeah. So I'm looking at these images, and you had some ALMA images. My recollection is that from the lensing studies that you often see large clumps, and I'm not seeing them at least in this TNG image. Do you see big clumps in the ALMA images directly?
So I don't have them here with me at the moment. So yeah, some clumps are seen in the lensing. Certainly, clumps are seen. There's still an ongoing debate if star formation is clumpy or not, and what it mostly has to do with And this is also actually, if you look, for instance, well, you could look at any image here, but if you look at the bottom ones or so, what you're picking up is that quite frequently they're very bright in the center. So you have a very bright compact thing, and you actually would need to integrate deeper to reach the surface brightnesses to really securely say if it is indeed one or two very bright clumps and there's not that much of emission under it or not. Quite frequently, observations have a detection of a signal to noise ratio of 4 or 5, which is already a significant investment of time, but clearly there's room for improvement there. So there are some clumps seen, but there are also many examples where there is no clumps seen. So the debate is still out there. I think it will require more than the 5-6 handful of examples that I know that have fairly high resolution.
Right.
And it, in some cases, will also require going deeper.
So I recall, as you say, that there's very few examples. Is there any correlation between the star formation rate and the clumpiness that you know of?
Well, I need to think hard now. So what comes to mind is work by Wipu Rujupukaran. I'm fairly sure I'm mispronouncing his name. He's based in Thailand. So who has looked at the dust continuum distribution of some of the most actively still main sequency galaxies. And there you don't really see clumps. What you do see is if you look at the brightest sub-millimeter galaxies, that's work by Jackie Hodge and Callisto Rivera and others. So if you look at the brightest sub-millimeter galaxies, the most active star-forming ones, and even some of the lens ones, there you certainly see some clumps, or actually what you see quite frequently, which is also quite exciting, is that the locations where the dust continuum emission is offset from the locations where the UV emission is.
Yeah. And
this may very well just be, complex dust geometries, where some of the emission is coming out through a channel in the UV where there is no dust obscuration, and other locations the dust obscuration is so strong that just no UV emission is coming out, or hardly any. But there you see clear mismatches in geometry, which must have something to do with more complex dynamics driving high densities of gas and star formation, which could become clumps. So this is seen in really the most active star forming ones, but not so much in the normal, whatever normal is.
Main sequence sort of
main
galaxies,
sequence galaxies.
So let me also, just to follow up on that, I mean, the ALMA observations also, as you said, often get CO at the same time, right? Are they spectrally resolved, the CO lines? Can you see the rotation curve, and then on top of that, can you see the dispersion, or is the dispersion not believable because it's beam smeared?
You sometimes indeed get CO emission as well. Spectral resolution is typically not, is sometimes an issue, sometimes not. The real game changer here again is spatial resolution. I think the most interesting results recently, or what comes to mind, is work by Francesca Rizzo, who used lensing to actually be able to resolve galaxies down to 100 parsec scales. She didn't use CO, but she used C2, and what she finds is, and because she's reaching these high angular scales, beam smearing is less of an issue, and she then has the full modeling feature to deal with this as well. And there, what she finds in redshift 4-ish galaxies, actually quite ordered rotation, so that these galaxies are rotationally dominated, supported, and not, so the velocity dispersion is actually relatively small compared to the rotational velocity.
So I think I've just seen that. Yeah, that which was very striking, because I mean, there's these old results from Genzel's group where you claim that that high redshift, particularly larger star forming galaxies, were very much dispersion
Absolutely, but I think there's something relevant here to ask yourself, which is, so there's two items. One, what Francesca did and also Marcel Neleman is Redshift 4. What Reinhard Genzel and his group, Natascha Förster-Schreiber, mostly did was Redshift 2, but also a very big difference is CO, or ionized carbon, which traces gas around molecular clouds, which is what ALMA provides you, versus what Förster-Schreiber and Genzel and so on did, which is based on H-alpha, where you're looking at optical ionization lines, which actually come from different ISM components, and maybe even further out in the galaxy or higher up, farther away, blown out from the galaxy. So a very relevant question that is not yet answered and should be answered is, if you take the same set of, if you take a galaxy and you derive its dynamics from optical ionization lines and from molecular emission lines, do you get the same picture? Yes or no? Is that different gas tracing the same dynamics or not? Or do they really come from different regions? And that's a question that has not yet been answered.
Now, you could carry out those same observations at Redshift 2, I gather. Maybe not the C+. I guess you'd have to then probably rely on some CO line to fall into the right
and that
frequency.
CO is fainter, so then the investment is more. So you need significant amounts of observing time. You need about 40 hours per galaxy to do this property. And that's, we've been trying to convince the TAC, but they're still.
Well, okay, good. I'm glad you're trying to do that. I'll try to convince them too.
Good.
Thanks.
Any other question from the audience? I may want to ask a question. So, so about deep blind survey. So, which ALMA band is currently most popular? Like, it's 870 micron, 2 millimeter, or 3 millimeter?
Well, it depends a little bit on the question that you're asking. So the typical workhorses in dust continuum are band 6 and 7, which corresponds to observed wavelengths of 870 micron and 1 millimeter. And the reason is that it sort of is a sweet spot, because as you go to shorter wavelengths, galaxies are brighter, and if they're brighter, they're easier to detect. But if you go to shorter wavelengths or higher ALMA bands, then the sensitivity of the instrument itself becomes less, which means that to actually detect a galaxy, you need a bit more time.
Yes.
Secondly, the field of view of the galaxy towards shorter wavelengths also becomes smaller. So with the same amount of observing time, you're covering a smaller area on the sky. So there, the question is, what is your survey speed? And then typically band 6, 7 has been seen as sort of the sweet spot. Galaxies are bright enough to pick them up easily. The instrument is still sensitive enough. Weather requirements are not too complicated, etc., etc. Now, there has been a strong push towards longer wavelengths, especially 2 millimeters, because it has been argued that although the galaxies are actually fainter there, your field of view is larger, but it has been argued that by looking at 2 millimeter, you're preferentially picking up higher redshift galaxies. So what you're doing is that you're filtering out. This is just how the SCD moves through bands as a function of redshift. It moves through frequency space as a function of redshift. The idea is that you're picking up preferentially higher redshift objects and quantifying the dust obscured star formation in redshift in galaxies above redshift 3. That's really the unexplored territory. And for that, maybe redshift, maybe observations in band 4, so 2 millimeters or so, or more sensitive than at shorter wavelengths. But it always comes at a cost. So it depends a little bit on the science question that you're asking.
Yeah, because I'm interested in 2 millimeter and 3 millimeter, because those are like the bands that the redshift distribution function actually peaks at VOR, the cosmic reionization effect.
Yeah, no, certainly.
Yes.
Certainly. Yeah, so especially Caitlin Casey has been pushing the effort, and Jorge Zavala have been pushing the effort of longer wavelength blank surveys.
Is there any like promising research you can do with a TNG box, for instance.
Sorry,
with TNG, like big box simulation.
Well, there's many interesting sciences that you can do with a big box simulation. You know, I think so. What I focused on in this particular talk with TNG is mostly individual galaxies, and I think zooming in more carefully would be interesting, trying to understand what type of structures you see in the galaxies, bars, spiral arms, and how they are formed, and confronting this with observations. But similarly, what we just talked about, what no one has been looking at in these type of boxes, because it's also computationally quite expensive to run radiative transfer over the full box, the full redshift evolution, is to get a feeling of the simulation can also give you a prediction of how many galaxies you expect to detect to begin with, and that can provide clear clues on how much dust there is in these type of galaxies. I think a quite relevant improvement would be having actual dust formation recipes in these type of models, or being able to actually cool the gas down to temperatures where the dust would shine to 10, 20, 50, 100 Kelvin. And there's many people working on this, on these type of improvements. And then, I mean, there's so many, just with the radiative transfer runs that I've done, there's a wide variety of science questions that you can answer related to dust itself. You know, how do attenuation curves in galaxies look like? How do they vary across galaxy properties, across cosmic time, etc.
Yes.
And many more.
Thank you. I think we are running a bit out of time today, so thanks for the audience. I think we should conclude at this point now. Yes, those who have more questions and want to stay for a few more minutes, please feel welcome to stay. And otherwise, see you next time.
Thank you very much.